Hi, I'm Michael. I'm a Prometheus addict. I work in the cloud platform team at Red Hat, and
Hi, Michael. So I'm Frederic. I lead the monitoring team at Red Hat, previously CoreOS, and I basically work on anything Kubernetes and Prometheus and anything in between, which is also why I work on the Prometheus operator, for example, because that connects the two worlds. So, but today, concretely, we want to talk about autoscaling everything on Kubernetes with Prometheus. And before we really dive into how all of that works, let's make sure we all understand what we mean when we talk about autoscaling. So let's make sure we're all on the same page. So on an abstract level, autoscaling is really about calculating the resources that we're going to need to cover the demand. So really, why all of us are working on infrastructure is because our companies need to make money somehow, right? And we are the ones that provide resources to the rest of our companies to do this and to satisfy all of that. And really how demand is measured is by metrics. And obviously we do that with Prometheus, which is why we're here. And in order to actually make use of all of these things, we need to collect them, we need to make them queryable, and we need to store them to query over time. And what I started with is we ultimately do this in order to fulfill our service level objectives of our service level agreements. So that basically means that we've promised our users some sort of availability, or really whatever your service level objective is. If you want to know more about these things, I highly recommend reading the Google SRE book. There's loads of examples, and even in the new workbook, there are examples based on Prometheus and even Prometheus metrics, queries and alerting rules and all of that. But yeah, basically the objective means I am promising my user 99.99% uptime or availability. That's the SLO of the SLA. And the indicator could be the combination of multiple services availability, or really anything that influences that objective. So now we know on an abstract level what autoscaling is and why we do it. Now in Kubernetes, what does that look like? In Kubernetes, we really have two high-level kinds of autoscaling, and one of them is not really autoscaling, which is why I'm going to start with that, which is cluster-level autoscaling. So sizing our cluster based on demand. And why I'm saying that is because in Kubernetes, this is not really based on any metrics. In Kubernetes, cluster autoscaling works by the scheduler attempting to schedule a new pod, so some workload, and it doesn't fit into our Kubernetes cluster anymore. And if that's the case, and adding a new node would solve that problem, then we would increase the size of the cluster. Whereas the application or the workload autoscaling within Kubernetes actually does work with metrics over time. And that's what we're going to be taking a closer look at. And the two subcategories within that we focus on in Kubernetes is horizontal. So how do we horizontally scale our workloads, and how do we vertically scale those? And I'm going to talk about that a little bit more. So in Kubernetes, we call this the horizontal pod autoscaler. And really the resources that we are scaling here, because remember, we said autoscaling is sizing resources based on demand. The resources we're increasing or decreasing here are the replicas of our workload. But that means that our applications actually need to be designed in order to be able to scale them this way. And sometimes in the Kubernetes world, people call this cloud native applications, when applications or stateful applications are able to do this. And really what all of that means is that we can increase or change the amount of replicas based on demand. But our applications need to be designed that way. But there's a lot of useful applications that are not cloud native or do not work in the way that we can just add more replicas and we decrease our query latency or something like that. And that's fine. There's loads of perfectly good databases out there that do not scale to planet scale and that are still extremely useful. But those kinds of workloads still need to be sized appropriately. And that's where vertical autoscaling comes in, and we call this the vertical pod autoscaler. And so here we size the resources, really the CPU and memory that is available to that pod or workload. And as I said, this is less complicated for the actual workload to be designed because it will just really use whatever it will use, right? And we, with vertical pod autoscaling, make sure that it will get the resources that it needs. However, that does mean that the autoscaling mechanism itself is a lot more complicated. And we'll see later why that is. Now, let's just take a look at how all of this historically worked in Kubernetes and how it works today, because it has evolved over time. So within Kubernetes, there used to be this, or still is, this component called Heapster. It is, as of this release cycle for Kubernetes, deprecated. And Heapster went to all Kubernetes nodes and collected metrics from cAdvisor. So every 60 seconds, it went to all the Kubernetes nodes and collected all of those metrics, and then wrote it into some time series database. And this was how every single system had to work. And I think by default, InfluxDB was like the metric sink that was being used here. And yeah, that worked fine in this kind of architecture. And we could autoscale. Woo! But if you noticed, because of this architecture, we really fundamentally were not able to use Prometheus for this, which obviously makes us sad. So enter resource and custom metrics API. So we realized that this architecture won't really work. And there were a variety of reasons why this architecture in the first place was suboptimal, primarily for maintenance reasons. So all the metrics things available in Heapster were actually in the Heapster code base. And so what happened a lot was that some vendor who really wanted Kubernetes support came along and implemented that support and just abandoned it afterwards. There's no bad intent or anything, but this happens. And we said, when we get to redesign something like this, we need to make sure that this doesn't happen again. And so when we designed the resource and custom metrics API, we really wanted to make sure that we are not owning the implementation of these APIs. We are really just specifying well-known APIs so that when someone wants support, they will own that part. And so that's what we did. And we have these APIs, and they're well specified, and there is a Prometheus adapter. So we can now autoscale on Prometheus metrics. And just a fact about these APIs as they work today, they just return a single value. So basically, like an instant result, like the last entry in a time series. And that's basically, down here you can see the architecture of how that works. So the Kubernetes API has a mechanism called API aggregation. So we register the Prometheus adapter at the Kubernetes API. And whenever anyone asks the Kubernetes API for metrics, it will forward it to the Prometheus adapter, which converts it to an actual Prometheus query, and then returns the result for that. So now we can actually use this to horizontally scale our workloads. But it turns out this is not quite enough for also vertically autoscaling. And this is where Michael comes in and tells us why.
Say vertical pod autoscaling? Woo! Thank you. Yeah. Okay. All right. So we learned so far how the basic metric stuff goes down, especially how it goes down with horizontal pod autoscaling. And now we're going to have a closer look, including a demo around vertical pod autoscaling. So first off, we're going to do the demo. And who of you has been around last year in this place? Okay, so you might have seen me failing in the lightning talk, so play it safe this time. I'm going to play a video. Yeah, not that stupid. Now all I need to learn is how to operate VLC. Yeah, I know, right? Shouldn't there be a full screen?
Double click on just on the video itself.
All right, we're good. Okay, so we decided that we're gonna first show you the demo and then explain what happened. So we have here a, as the Kubernetes distribution we're using, obviously OpenShift. We have the VPA set up, comes with a couple of components. I'm gonna talk about that in a moment. And then we have obviously Prometheus delivering us the metrics here. And we have a very simple setup, a deployment that initially has a certain request set for CPU and memory, and then the VPA kicks in and comes up with a recommendation. So let's have a look at that. So we have in the VPA namespace, we have a couple of components here. We have Prometheus here and another namespace running, and the actual target of the VPA that we want to scale vertically. So if we have a look at that, you see in the upper part, you see the actual VPA definition that essentially all you really need to have a look at is that label. So every pod, no matter what the owner is, that has that label, in this case app hamster, will be vertically scaled by this VPA here. And then we have the deployment, initially 2 replicas, and if you look down there, resources, requests, we have CPU and memory, right? One of the issues you might wonder, how do I arrive at these initial values? I'll come back to that in a moment, but that's the starting point, right? And now we gonna tell Kubernetes, go ahead and apply that. This is the desired state. Go off and, in this case, kubectl create. Kubectl apply would have probably been better. It creates these resources. The deployment kicks in, the 2 pods spinning up. And if we look into the pods, then we will see that we have initially, as we requested, the 100 millicores and the 50 megabytes, right? Okay, so now VPA says, well, I'm supposed to look after these pods because they're labeled with app hamster. So let's have a look at what the VPA says. Not much so far, right? Just says, yeah, I'm aware of that, but I don't really know anything about that. Without being able to observe these pods and what they're consuming, VPA can't do anything about it, right? It just needs to learn first, what is the actual usage. And after some time, and now we could be talking about cats, or we have a little bit anti-cat pattern today, right? It takes a little, and maybe this is one thing to note. Here I'm using the update mode auto, essentially telling the VPA, hey, you decide how to update these pods. You can use other modes, but initially this is the default and probably in this stage wise to use. And at some point in time, if we look at the pods there, we will see that VPA comes up with a recommendation and says, hey, I noticed you're actually using that amount of memory, that amount of CPU. And if we look at the VPA again, you see it down there in recommendation part. Hey, I figured out this is the lower bound, this is the upper bound, and this is the target here, right? And this is the part where you then can say, well, thanks for that recommendation. I actually want to apply it, right? And that's what's going to happen. So the updater will, based on the policy here, take that and actually update the pods. And again, after some seconds, the pods will have the new requests set. So in terms of the UX, I guess we try to keep it as simple as possible. The very well-known established pattern of opt-in by labels and creating this VPA. Yes, you do need infrastructure, but who doesn't love to deploy and run Prometheus there? So it should be rather straightforward. I think I've bridged the time that the pods are actually, yes, now we have it here, right? So if you now look here, you see that the new requests for CPU and memory are in place. And that's pretty much it. Now, the question is, why are we doing that? And how does it actually work? So we had a look at that already, right? YAML. We are in Kubernetes land, we are YAML engineers, first and foremost. The more advanced ones are already using JSONet, but most of us are still doing YAML. And that little innocent part of the YAML file is really, it's an optional thing. And people often go like, I don't know, I have no idea how much CPU or memory I should put there. I just leave it out. Why not? Before we get into the why and how, a little bit of terminology and background. Who of you, I asked it last year as well, who of you is familiar to a certain extent with Kubernetes? Show of hands, please. That's less than last year? Okay, so it's like 30%-ish? Okay, that's more. So what does, on a certain level, what does Kubernetes really do? Well, the nodes, they're offering resources, right? Like CPU, memory, and so on. The pods consume these resources. They burn the cycles. The scheduler matches the needs of the pods, placing them on certain nodes that fulfill these needs. CPU and memory just being two kinds of resources. There are obviously others in terms of machine learning. GPUs are important, and they're disk and many, many more. But for our considerations, only CPU time and memory is of relevance. There are different types of resources. Some of them are compressible. For example, CPU time, if I take away CPU time, it would just run slower. If I take away memory, well, I might be taking away the wrong page and you might be dead. So that's incompressible. And Kubernetes has the notion of equality of a service. And here you might start to see that it's kind of important that you're actually setting these requests. So requests is what the scheduler uses to determine which node I can, or the scheduler, can use to place the pod, to run the pod and tell the kubelet locally, hey, run that pod for me. Limit means this is the absolute limit that this pod, or actually on the container level, can use. If you set the limit and the request equally, it says, as I said, limit is not used by the scheduler, only the request. If you set it equal, then you have a so-called guaranteed pod. If you have a request set, which must be greater than 0, and you have a limit which is greater than a request, then you have so-called burstable resources there. And best effort essentially means, well, you're lazy. You're not setting either. You're not setting the limit, not setting the request. And that is where, when I initially said, this is optional, well, kind of, right? If you don't care about the quality of service, then yeah, it's optional. Most of us kind of do, so I would say you're probably better off in the burstable or the guaranteed case, depending on the use case. All right, motivation. This is not something that we came up with, we as in the Kubernetes, contributors or community or whatever, but this is really driven by users. Yes, as with many, many other things, Google had that for forever, I guess. Autopilot there, and the design is certainly informed by that. But these are real-world users out there that were literally, complaining about that, and rightly so, right? They said, well, you got to do that. You got to set the request there, but how are you going about that? Do you do that manually? Can you do that manually? Does that make sense? And I do encourage you to read these blog posts. I just pulled out some specific parts that are relevant here. But this is really the motivation to say, well, obviously we need to provide something there, and luckily we have with the autopilot work of Google, we have a blueprint there, a way how to go about that. So the goals, why, what are we aiming for? Obviously, it's about automation. So you want to free people to not do that manually. Because manually, settings there, it's like, well, I think it should be 2 gigs and whatever. So you either provisioning for the worst case, which means a lot of waste, because you're expecting this amount of traffic, and that's what you're putting there in the request. So this is brittle and hard. So people either, as I said, because it's optional, don't care, or because it's hard, they don't do it. But as we've learned, if there are no requests set for the container, then you end up in best effort, right? On the other hand, you also want to improve utilization. I'm not arguing for 100%. No one should be doing that, because that means that in case of failure, if you're upgrading a node or whatever, that you don't have any wiggle room left to compensate for that. But you might want to aim for, I don't know, 60%, 70%, whatever. So you allow the scheduler to better bin back, and there is also an impact on other functionality within Kubernetes, for example, the out-of-resource handling. Because if a node starts to, running out of resources, there's a certain defined protocol in there saying like, well, first I think it's priority, and then it's around the QoS classes there. So, and maybe in future, I'm not entirely sure if anyone knows about that, where we are with the optimizing scheduler, that you can actually reshuffle, proactively reshuffle pods. That might also be a case. But for now, it's mainly, you want to automate that. You don't want people to manually guess, more or less guesstimates put in there, and you want to improve utilization in a nutshell. Use cases. Whereas we earlier heard the HBA, the horizontal pod autoscaler, is probably best suited for stateless apps, especially the ones that, if you horizontal can scale them, you get a better performance out there. If you have a stateful app, for example, you have your WordPress that encapsulates MySQL, I believe, by default, or you have something like a single node database or whatever that benefits from adding 1 minute. What? Wow. Okay. What? Okay. Yeah. Legacy apps. This is the API server. We're talking about the API server. This is the part where the, oh, Jesus Christ. 1 minute? Didn't we have 40 minutes? Where the request comes in and you can actually mutate the request there. And the basic idea of the VPA is you observe the resource consumption, you build up that historic profile through the recommender, you apply that to pods through the labels, which is the updater, and that is how it looks like. Probably not the easiest thing to digest. Most important thing here is storage. History storage, that is where Prometheus comes in, because as we've learned early on, the API server there, or metric server, really gives us just the point in time there. And then you have the VPA controller that looks after the VPA objects, and the admission controller that was in the previous bit, where it interjects in the API server and updates the spec accordingly. Limitations, this is really early days, it's pre-alpha. So my ask to you, or our ask to you, is really, please beat the crap out of it, test it, tease out edge cases. We really need feedback. There's one part which is currently, due to different reasons, container runtime support and so on and so forth, you can't in-place update, so it will create a new pod, which sucks, obviously. Also, around usage spikes, it's unclear how to deal with that best so far. Okay, have a look at the issue, the design. Please provide feedback. Join SIG Autoscaling. We're lovely people there. And SIG Instrumentation and SIG Autoscaling work together towards a unified historical metrics API. Big shout out to Solly Ross, who put together the screencast there of the demo. And I think with that, that's it.
Well, thank you. We have 4 minutes for questions. Put your hand up. That light's very bright as well. Okay, I can actually see any hands. Oh, there's one at the back. So you're nice to meet having all the same side.
Hi, thank you so much for the talk. So I think you roughly addressed this real quick there at the end, but maybe I was going to ask you to maybe explain a little bit more about how you're thinking about hysteresis in terms of scaling up and down rapidly, especially if we can't do in-place updates.
Really good question, and I guess the answer in a nutshell is there is the design document that specifies how things should work. There is the current code, but it's so early days that unless we get testing and feedback from outside the usual suspects, we're doing that, and we're probably blind to that or biased, very heavily biased to our workloads, our use cases. So for now, this is certainly not anything that you can use in production. Again, this is pre-alpha, right? It's not even part of that release cycle yet. But what should be happening once the in-place updates come in place, that you essentially also, and I believe also Google does that, essentially project, you say you're on a certain trajectory, it looks like you're going up like that, so I proactively give you a recommendation where you then again can opt in, say, yeah, apply that, or yeah, ignore that parent spike. But again, this is really, really, it very much depends on what you can do, what you can provide us in terms of feedback, right? And anything, and if you say, hey, this is crap, right? This is crap design, also good feedback, right? Because we really, really, really don't know yet, other than the code that you can try out yourself, would that really work for the majority of people? It is definitely a problem, and there's that motivation, a strong motivation there, but is it the right solution? Is it the right UX or whatever? Please tell us.
Just what part of the question that you asked, like basically how to prevent over autoscaling, like autoscaling too often. This is already solved in the HPA, kind of at least. So at least for scaling down, there is a like a cooldown, which is larger than the one going up. So you can always more easily scale up than you can scale down, and it's just a safety mechanism. I can imagine maybe something like that could be possible for the VPA as well.
Okay.
Again, it really depends on the kind of resource you look at. If you have a non-compressible resource like memory, you kind of like, stuck there. Sorry.
Okay. And how it's integrated with HPA and Prometheus?
So currently, I would say don't necessarily use HPAs and VPAs together. And Prometheus integration is exactly that here, right? So the metric server, always gives you just this one point in time, this one reading. So you need something, a time series database, sounds familiar, that actually allows you conforming this data API there, which will be the historic. What's the official term?
Like there is no historical metrics API defined yet, and that is why SIG Instrumentation and SIG Autoscaling are going to be working together to do that, because really only SIG Autoscaling is a use case for that right now.
So the integration is not fully there yet.
No, there's just, we know that we need this and we want to design it, we just haven't gotten to it yet.
Okay, and we are out of time there, so thank you very much.
Thank you.